going yet? Okay, what happened to the titles? Did I see the titles? They happened? Okay, good. So what we're going to do today, folks, is don't forget the DVDs are available for checkout. There have been a lot of absences due to illness, so some of the DVDs, we only have 2 of them available for checkout, and some of them are checked out. So you just come over to the Resource Center, see if they're available. What we're going to do today is go on with rational functions. I gave a very brief introduction during the last class session at the end of the session, and so what we're going to do now is go ahead and go into more detail about them. And this will help deepen your understanding of polynomials, because what a rational function is a fraction of 2 polynomials, or a ratio of 2 polynomials. And some of the things that we're familiar with in general about graphs are y-intercepts, or y-intercept, possible zeros, and then we've also, throughout the course, we've been talking about the end behavior, and you need to be real clear on what that is. When you're building a graph, it's going to be if you're way off for large x values, or way off to the right for large x values as x approaches infinity off to the right, how's the graph behaving? Or if you go way off to the left. And notice what I did today is I show going to the right to sort of indicate you're heading towards a positive large value of x, and then I wrote the arrow coming to the left, thinking on your number line moving way off to the left for negative x values. Okay. Back in the control room, you guys have a couple of the monitors on some kind of other station. Can you guys get rid of that stuff? That'd be handy. Thanks. And then there's something new that exists with these things that you may have heard of before, something called asymptotes. And there are vertical asymptotes, and then there are horizontal asymptotes, and then there are what are called oblique or slant asymptotes, which are like linear functions. And we'll discuss what those are. Matter of fact, we'll get into that right away with a real simple, one of the most elementary rational functions that we've actually seen already earlier this term. So let's start simple, and then we'll build up to more sophisticated rational functions. The simplest one is what's called the reciprocal function. And what it is simply, let's write it just as y equals 1 over x. Y equals 1 over x. If you, and I'm just going to draw a small sketch of this elementary one. We talked about this in a previous session. If we start plotting points, means that it's something new for us, then we can just numerically imagine building a table of values. You can do it by hand for different choices of x, and then go ahead and plot the y values you get here. So for instance, let's just talk our way through it. If x equals 1, y is going to be 1 over 1. If x is 2, y becomes a half. If x is 3, a third. If x is 4, a quarter, and so forth. Does it ever hit the x-axis out there? No, never will. If you're out at 1,000, it's going to be 1,000th. It'll still be positive, but it's going to be very close to 0. Very close to 0. So the graph is coming down like this and passes through that important point 1, 1. What we say out here, as x approaches infinity, looking on your number line, y is approaching 0 from the positive side. And see how I put a little superscript there with a plus sign. That means this is a number very close to 0 but slightly positive. And you can see that on the graph as being like an airplane coming in for a landing here. This becomes less and less and less the further out to the right you go. The graph is approaching that line as you move out there. And so the equation of that line is y equals 0. Y equals 0. And that's called a horizontal asymptote. Okay? Now, let's examine what happens as we let x come in close to 0 here. X becoming close to 0 now, not y, but x. So I'm going to be coming in from the right side here. Now watch the way I can write this. I can say I want to let x approach 0. Again, let's make it approaching 0 from the positive side. Notice I'm dealing here with positive x values, not y values. I'm talking about x now, left and right. So as I let x approach 0 from the positive side, what I'm doing is trying to figure out what this graph does after we pass through, coming to leftward, after it comes through this point 1, 1, as we come in towards this. And so let's start plotting some numbers. This is at x equals 1 right there. So let's let x be a half. What's the reciprocal of a half? 2. What's the reciprocal of a third? 3. What's the reciprocal of a fourth? All right, okay. What's the reciprocal of a thousandth? 1,000th. 1,000. This thing takes off like a rocket. Does it ever hit this y-axis right here? Does it ever hit that? Can you put x equals 0 in here, folks? No. You cannot put x equals 0 in. That's not in the domain of this thing, is it? Okay, so this, notice, is another idea, or another line that the graph approaches. Happens to be a vertical line, and the equation of that thing is x equals 0. X equaling 0, and that's called a, if this is a horizontal asymptote over here, this thing's called a vertical asymptote. Sure.
Why are you saying that x is never going to equal 0 and then you think that x equals to 0?
This is the equation that line can't be. It cannot be this. But if somebody asks you, what's the equation of the vertical asymptote, you're going to say x equals 0.
Because it gets so close?
Yes.
Okay.
It doesn't get there, though. It never gets there. That's why we use this word asymptote. Well, those are perfectly good values in the domain of this function.
Oh, because it's a value.
Yeah. Now, why don't we nail down the domain while we're at it? Could we drop negative numbers in here for x on this function, folks? Negative numbers, perfectly fine. Right? Positive numbers, perfectly fine. We saw those. So everything's good except putting a 0 in there, right? So the domain, using our interval notation, always smaller on the left to larger, coming from the left, negative infinity up to, but not including 0, so we use parentheses. Then we pick up microscopically on the other side of 0 and carry on to the right for our domain. How about the range? How about the range? How low can these numbers go? Well, notice I have not plotted anything on the left yet, have I? Okay, watch this. Let's call this thing f of x. Let's do a little quick review. If I formed f of minus x, that would be 1 over negative x, right? 1 over negative x, which is the same as negative 1 over x. But what also would then be the negative of f of x? If I put a negative out in front here, negative 1 over x. Notice that these are the same. That tells us what about the function? It is an odd function. It's an odd function. Now we've talked about this function earlier, previously. I'm just coming back through it again because typically you only hear about 30% of what gets said or presented. Graphically, here's our original f of x. What would this do to the graph of f of x? What would putting a negative in front of it do to the graph? What's it do to the y values, folks? If you put a negative in front here, the y's become negative. Don't you turn it upside down? Okay, so this would be upside down. If you turn the graph upside down, and versus doing this, what does this do to the graph? No, it doesn't shift it. It turns it over the y-axis. Turns it over the y-axis. Those graphs will be the same. So think about that. We spent all this time plotting this wing of this function, and we didn't finish. But we did examine the fact that this thing is odd. So if I took this graph and turned it around the y-axis, it would be sitting over here, right? And if I took the graph and turned it upside down, it has to lie right on top of if I turned it this way, wouldn't it? So what that means is if I turn it around this way, there's a wing of this sitting up here. That would have to be the same as if I took the graph and turned it upside down. So that meant then that this piece up here would have to actually lie down here as well. If you did not understand that, all you have to do is plot points with negative x values. If you put -1 in for x, you get -1. If you put -0.5 in right here, you're going to get -2, etc. And if you go further to the left, like -2, -3, -2 would be -0.5. -3 would be -1/3, a fourth, -1/4, etc. And you get this wing of this function. Notice how I use dotted lines to indicate the vertical asymptotes and the horizontal asymptotes. Okay, this is an elementary function. It's a very important one, y equals 1 over x. Down here, let's do one more. 1 over x squared. 1 over x squared. Do you agree if I call this thing f of x again, that f of x will be the same as f of -x? If I replace x here with -x and square it, it's going to come back to be the original. Everybody comfortable with that? They're the same thing? Okay, so that means we have what kind of symmetry here? Y-axis symmetry. So this is going to be, this thing is going to be an even function. An even function. This one over here was an odd function. So let's plot some points. If x equals 1, y equals 1. If x equals 2, it's going to be 1/4. It goes down faster, folks, compared to that other one. It goes down faster. 1/4. If you're at 3, 1/9 instead of 1/3. It's got that same kind of characteristic, doesn't it? And so what we're going to get, and if you put in a half here, what's the reciprocal of 1/2 squared? Let's see, a half squared is 1/4. The reciprocal of 1/4 is 4. So this thing's going to take off faster than that other one did vertically and drop quicker. And it's an even function, so without having to do any more point plotting, this thing's going to have y-axis symmetry. It's going to lay right in here. Do you notice asymptotes here? Asymptotes. There is a vertical asymptote, and you want to make sure you dot that on there. And then what are you going to write down? Somewhere near it, you write down x equals 0, a complete sentence. And then instead of writing out those words, vertical asymptote, all the time, what I typically do is I just write v period a period next to it. Don't just write 0 down, which is what half of you probably will do, okay? I've taught this course enough to know that, okay? It's x equals 0 is the equation of that line, okay? And there's another one here, isn't there? Okay, the other one is y equals 0, dot, 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 going off there. And That's the equation, and that's our horizontal asymptote. Even function. Easy. Reminds me of, let me get in the camera, reminds me of a conductor. Okay? So just think about that, 1 over x squared. Every time you see an orchestra and the conductor playing, just think of your algebra class, okay? All right, okay. You don't see the conductors doing this very often, though. Okay. All right. So what we have going on here are two rational functions. This is a 0th degree polynomial. Think of x to the 0 up on top there. 0th degree polynomial divided by a 1st degree, right? A 0th degree polynomial divided by a 1st degree polynomial. Over here, we have a 0th degree polynomial divided by a 2nd degree polynomial. Okay, we're getting excited now. I don't want you to forget transformations, though. Remember how we stretch graphs and shrink them? Stretch them by putting a multiplier on the function, right, to double its height, say, or triple its height, or squeeze it, okay? And then we also learned how to shift a graph, left and right, up and down, starting back at the beginning of the course with circles. Okay, so let's make up one, a variation on that first one over here. So let's do this. Y equals 2 divided by x minus 1 plus 1. Don't get nervous. Do you see that this is really what function without its transforms? It's 1 over x, isn't it? This is like y equals 1 over x. Let me call this function that we're playing with here r of x for rational function, r of x. Okay. Now, you should be able to tell me what transformations have occurred to this thing. The first transformation is a distortion, a change of the shape of this elementary one that we just went over, by putting a multiplier of 2 on it. So think of this. Isn't this going to be twice as tall, folks? And this is the same algebraically as 2 divided by x. So that 2 that you see up here, that 2 up here is going to be a vertical stretch factor by a multiple of 2. It's going to take that graph we went over just a couple minutes ago, that reciprocal function, and it's going to stretch it, make it twice as tall. Everybody feel good? Okay with that? The sketch of that compared to the 1 over x graph, if that's 1 over x dotted there, by doubling the height, instead of that 1 being a height of 1, it's going to be a height of 2. And everywhere else, it's going to be twice as tall. Everywhere else, it's going to be twice as tall as it was. Okay? See that? So this would be roughly a sketch of 2 over x, where it's twice as tall. Okay? Twice as tall. Is that all right? I hope. Next step. Remember, we're looking at this weird looking thing up here. This causes now, after you distort the graph with this multiplier of 2, this causes that graph to get somebody, let's see, there's about 2 or 3 of you that talk up all the time. I want to hear from the rest of you. Shifted to the right, 1. Very nice. And this is my little code I like to write down. So if I take a break and come back later on, I don't have to think. I can just look at what I wrote down here and I know what I did, what should be going on. And then finally, somebody else, adding 1 to the tail end of this. What's that do to the picture? I could take this drawing 2 over x and I could slide it 1 to the right, right? And then the plus 1 takes and adds it 1 to all the heights, doesn't it? So it's going to take the original graph, 1 over x, it's been stretched twice as tall, slid 1 to the right, and lifted up 1. Okay. Keep your eyes open for these kind of transforms when you see problems in your book. Mm-hmm.
Does that make the horizontal asymptote y1?
Everything goes with it, doesn't it? Everything goes with it, yes. So what's going to happen is the whole thing gets slid to the right, lifted up 1 after it had been stretched originally. So there's also a vertical asymptote as well as horizontal. So finally, to make a long story short, the final sketch of this thing is the asymptotes that were originally your x-axis and your y-axis get slid to 1 to the right and lifted up 1 also. So I would probably draw those first and label them like this, and take and do my same thing with my vertical asymptotes and label it. And then I would lay my graph on there that we've talked about, but make sure that you have vertically stretched it by twice as much. That's why you need to come back and think about what happened originally back here. So we're going to take, and instead of it going through this point right here where the asymptotes meet, would be at 1, 1, right? Instead of being over 1 and up 1 from there, and 1 to the left of that and back down here, it's going to be twice, it'll be twice as tall there. It'll be twice above, it'll be 2 above the axis, the asymptote there, instead of 1 above it. And then it's going to work its way down from there. So it's going to be looking like this compared to the 1 over x type of graph, which would have been right in here, like this. So this graph is going to be, the true graph is going to look more like this, darkened here. And I don't know if you see this or not, but look at this y-intercept, folks. I think it should be 0, -1. And this x-intercept, the 0 of the function over here, should be at, I believe, -1, 0. And an important point over here would be at what? What would that spot be if you were listening to what I said earlier? 1 to the, shifted 1 to the right, you go 1 more, 1 to the right plus 1 more is 2, so x equals 2. And the y value, this gets you up on the asymptote by going up 1. And normally you'd be up just 1 above that, but actually we've got a stretch on there making it twice as tall, so we actually have 2 plus the 1 is 3. How can we check those points? We can try putting those inputs into our r of x up here. So let's try putting -1 in for our input. Put -1 in, I get 2 over -2 plus 1 is 0. Checks. -1, 0 works. I try putting a y-intercept, x equals 0 in. I get 2 over -1 plus 1 is -1. So I get 0, -1. And another point to check is out at 2. And I drop a 2 in, and I get 2 over 1 plus 1 is 3. So I used our understanding of transformations to draw a sketch. I used our understanding of transformations to draw the sketch, and then I nailed down a few key points, and then I spot checked those by going back and dropping them into the function to see if we got it. On more complicated ones, you could then, after you did your mental work on transforming this and believing what you've got is correct, is kick it into your calculator and see it that way. Okay? Any questions? You can see how this course builds on stuff that came earlier. We've got this vocabulary of end behavior. See the end behavior? Y approaching 1 as x approaches infinity, off to the right, and similarly off to the left. We've got these asymptotes, a little bit of new vocabulary in there. We've got these transformations existing in here as well. We've got zeros. This function only has 1 0, it looks like, doesn't it? 1 0, and it does have a y-intercept. Question? Mm-hmm.
Does it matter if you mention your x or y first, like x approaches infinity as y equals 0 or something like that? Does it matter if you switch them around and say the
No.
y first?
No, it doesn't matter. It's usually better to talk about the domain readings first, though. Watch this. And actually, your question was good. She was asking, if it didn't come across on the video, she was asking about, do you mention the x first or the y first when you're talking about the end behavior or approaching asymptotes? It's usually better to talk about the x first. So watch the mathematics. This is a fancy way to explain, and we've actually already done this. But what I would do here is I would say x approaches infinity. That means I'm heading off to the right. I go back up and look at the original function and look at what r of x is doing. See if I can tuck it in down here. R of x, that original function, is approaching 2 divided by a huge number, isn't it? 2 over infinity up there. Because if you take 1, I don't know if you can see it, yeah. If you take 1 away from a huge number, that doesn't make much, that 1 doesn't make any difference, does it? No. Okay. And then we're adding 1 to that, right? Now look at what this combination is. Think about a number that is 2 divided by a huge number. That's really close to 0, isn't it? Isn't 2 over a huge number really close to 0? So the shorthand I like to use is, like I showed you earlier, is 0 with a little plus superscript. That's a slightly positive number close to 0. And we're adding 1 to that. Now look what happens in the limit as x does go towards infinity. In the limit, as x goes towards infinity, this approaches 0 and means you're adding a little bit to 1. Adding a little bit to 1 for these r values, which happen to be your y readings. So up here on the graph, if you can move the image up just a little bit, there we go. As you move further out to the right here, folks, here you're up 1, and the further out you go, you're adding less and less and less. That's what this mathematics indicates. And here it is graphically right there. Like the plane coming in for the landing. I'd like you to practice this a little bit when you see problems in the book, homework problems. Okay? Okay. Okay. Now, as we go off to the left here, let's do it similar to what I mentioned earlier. As we let x approach negative infinity, going to the left, then let's see what happens to r of x. We have 2 over a large negative number, looking up here, 2 over a large negative number, plus 1. And notice that this 2 over a huge negative number is what kind of number? Like 2 over 1,000, negative 1,000. 2 over negative 1,000,000. Very tiny again, near 0, but slightly negative, right? So the way I like to write that is 0 with a little negative superscript plus 1, and that's what your y is approaching. So check this out. As you come off to the left, going left here, going to the left, you're up at 1, and you're taking a little bit away from, see this? You're taking a little bit away from this 1. And the further out you go, you're taking less and less away. I like to think of something physical. You ever seen a fly come up and land on a ceiling upside down? Right? Coming in for a landing up on a ceiling? Okay, so you can think of it that way as you're going off to the left here. Finally, last comment about this, actually almost the last comment on this function, is what's the domain of this function? All real, you see, if you look at the picture, you can see it. Negative infinity coming over to 1, trouble at 1. Negative infinity coming over to 1, trouble at 1. Better skip that spot. Pick up microscopically on the other side of 1, and off to the right you go. Look at the range. How low? Start low, like water level rising. Good, good, good. Everything's good until you get to good. Y values from negative infinity coming up to, help me, 1, thank you. A gap there at 1 again. So negative infinity coming up to 1, trouble at 1, pick up just above 1, and continue on up. Okay, domain and range. Okay. Notice back now at the original for just a minute. This thing is a fraction plus a whole number. A fraction plus a whole number. In other words, we've got a fraction plus something else. Could we do something from beginning algebra with that? Couldn't we form this into a single fraction? It's just like you being back in elementary school, adding say, a fraction like 2/3 to 5, right? You need to get a common denominator and then build it into a single fraction. No different than what you did in arithmetic. So let's come over to this board. And do that. So we have our R of x is 2 over x minus 1 plus 1. Now I want to turn this into a single fraction. So I know that this is 1 over 1. My common denominator necessary here needs an x minus 1. So over here I'm going to multiply this 1 times x minus 1, top and bottom, so that I don't really change this thing. It's still the original function because all I've done is multiplied this last term 1 times 1. We all know that. And so now we have a common denominator. There's our common denominator, and our numerator is a 2 plus x minus 1, which we can simplify to x plus 1 over x minus 1. Okay. This is the way oftentimes you will see a rational function presented as a single ratio of two polynomials. In this case, we have a linear polynomial divided by a linear polynomial. Notice the end behavior. By looking at this original form, the end behavior. How do we examine end behavior? What dominates the numerator? X or the 1? If x is big. If x is big, Does 1 make much difference to it by adding 1? No. So that's what we mean by end behavior. X is big. Okay. What dominates the denominator? Again, X. Taking 1 away from a big number doesn't make much difference. Okay? So the dominant terms here, the dominant terms for end behavior as X approaches infinity is Y is approaching X over X. The leading term in a polynomial is what dominates the polynomial. We talked about that a few class sessions ago. The leading term of a polynomial dominates it. Okay? So it behaves like X over X if X is large. And then look what happens to that. X over X reduces to 1. So as you move further out, here's how you can see that horizontal asymptote. If the degree of the numerator is the same as the denominator, then all you have to examine are those leading terms, like I just showed you here. Examine the leading terms in the behavior. Feel good? Okay. If you went towards negative, and now the one thing this approach does not tell you very well is it doesn't tell you if you're coming up from below or above, like I explained earlier. Like the airplane coming in for the landing out to the right, or the fly coming up to the ceiling from heading off to the left. Okay. The detail, the way I explained that earlier, gives you that detail. Okay. So that helps you get your end behavior for a horizontal asymptote. We have a fraction here, and in the introduction to this last session, I spoke of the numerator as being a function called n of x, and the denominator being a function called d of x. Textbooks oftentimes will take the numerator and call it p of x, and the denominator q of x. Doesn't matter what symbols you use. What would make this fraction 0? What will make r of x equal to 0 if you've got a fraction here, x plus 1 over x minus 1? Doesn't turning that numerator into 0 make this equation turn to 0? Okay. Or you can just look at this problem now. Look at this problem. 0 equals this fraction. Multiply both sides by x minus 1, and you lose the x minus 1. Right? If you multiply both sides by x minus 1, it disappears. And you end up with x plus 1 equals 0, x equals negative 1. Negative 1 if y is 0. There's your 0 of r of x. The 0 of r of x. So the way you find zeros usually on on rational functions is you let the numerator function take on a 0 value. And that's how you examine where your zeros are going to occur. Okay? How are you going to find vertical asymptotes on rational functions? If you're given this function as x plus 1 over x minus 1, vertical asymptotes are places where trouble occurs, aren't they? Where trouble occurs in x. And I heard somebody mention it. If the denominator goes to 0, you've got trouble. Okay, so if your denominator goes to 0, x minus 1 equals 0, x equals 1 is a place for trouble. You go back and try putting a 1 in here, folks, into your function, and you get a nice 2 numerator over 0, which is undefined. So this is how you find vertical asymptotes, usually, is by setting the denominator equal to 0. So this is going to be vertical asymptote. There's a lot of new vocabulary with these things, and historically these rational functions tend to cause people a little more trouble. The first step in understanding them is know polynomials first. Know polynomials fairly well. Secondly is, once you know the polynomials well, become familiar by talking to each other with some of this vocabulary, like the word asymptote, both vertical and horizontal, so forth. Okay? Typically, textbooks will give you a series of steps to analyze polynomials and a series of steps to analyze rational functions. I cannot remember those steps. In order, I don't remember them at all. But all I do is I play with the thing. I play with it. I look for the easy things first, and then I start investigating it. And I try not to grab my calculator right away. Okay? So that's the way I would encourage you to play with these things. And also getting together with another person and talking it out is helpful. Okay, let's build another one. Because these things could get a lot more exciting than linear over linear, couldn't they? Okay, right? So, stay awake. Actually, you're probably so excited now you can't wait for the next problem. Okay. Any questions? Okay. We're going to work on this again tomorrow in the lab session. And then Friday, we're going to come back and do some more. So make sure you give this stuff some attention before Friday's session. Okay? And don't miss class tomorrow. Okay. Let's build one, a new one. Why don't we start with a factored form, just because that's more comfortable for most of us, if it's already given to us in factored form. Let's put a quadratic on top and a cubic down below. So we're going to have a numerator function and a denominator function, and we're going to put a quadratic on top in factored form. So what kind of zero might be a nice zero to have? X equals, huh? -3. So that means if x equals -3 for a 0, then that means x plus 3 would equal 0, right? So let's put that up there. Feel good? Let's put one over on the right side, say out at 4. At x equals 4. So that means x minus 4 could equal 0. So we have ourselves a nice simple quadratic. Down below, let's build a cubic. Let's say we have a cubic that has a factor that's going to have a vertical asymptote at, say, x equals, how about 2? A vertical asymptote at x equals 2. Then that means, what do we have to put in our denominator? We need to make what in the denominator will make this whole mess turn to undefined, because that's where vertical asymptotes occur. X minus 2, right? Let's give that factor, or the 0 on that polynomial of 2, let's give it a multiplicity of 2. Okay? let's lay another vertical asymptote on this thing. This is fun. So we're building the function. We're building the function up instead of just starting with some function given to us. So let's put one way off to the left, maybe over at minus, how about minus 6? If x equals minus 6 is another vertical asymptote, and I've got 4 minutes left. Okay. And so that's going to be an x plus 6 factor. Okay, so we're going to have zeros at -3, 0. Let's see if I can tuck that in, that information in over here. Zeros at -3, 0 and at 4, 0. And then we've got our vertical asymptotes already laid out here. So we got some good information from which we could start drawing some of this. Okay, so here we go. At 2, oh darn. At 2, we're going to have a vertical asymptote. At -6, we're going to have a vertical asymptote. I'm trying to model for you good behavior on your paper. Okay? You write the equations down, please. Okay. Now, we've got those two. Oh, we also have some zeros. At -3, we have a 0. And at 4, we have a 0. Okay, we've got 2 minutes left. You're going, he's not going to make it. Okay, just watch. Okay. Everybody okay so far? I've got the information down that we've got. Now, what are our leading terms going to be, folks? If I start playing with r of x here, expanding this out, isn't this first term going to be x squared? The leading term with some other stuff on here, minus x minus 12. And then down below, I'm going to end up with an x cubed leading term with some stuff. I'm not even going to worry about it. And look at this, folks. Isn't there going to be on the tail end of that cubic a plus 4 times 6? See it? Plus 4 times 6, 24. And so look what happens for x equals 0. r of 0 disappears the x terms, and I'm left with minus 1/2, right? So that's a point, 0 minus 1/2. Can I go another couple minutes? Okay. So 0 minus 1/2 is a y-intercept, folks, right here. Okay, now I'm going to go fast on this. Next class session, I'll come back and go a little slower. I want to draw a picture of the numerator. The numerator is a parabola, right? With zeros here and over here, right? Okay, so I'm going to just draw it kind of like this. It's going to bottom out somewhere. Whoops. It's going to bottom out somewhere in here probably. Right? So everybody agree? That's your numerator, your quadratic function here, n of x. Okay. Now, the denominator is an x cubed function. Up 24. X cubed up 24. And then look at this. This one, this polynomial in the denominator, this cubic, has a 0 at 2 and at -6, right? And it's x cubed behavior. Means it goes up right and down left as a cubic. And where does it bounce off the axis? At 2, because of the exponent being even. And over at -6, it cuts through the axis over here. Okay, so I'm going to try to draw it. How about just dotted? Comes up through. Let's see, what's it doing here? It's got to do this, doesn't it? Oh, a 2, not 4. Yeah, thank you. Thank God for erasers. Okay. So here at 2. So I'm drawing just the denominator function, right? Okay. Now, finally, in 30 seconds, we're going to draw this thing real quick, and then you could listen to this tape over and over again if necessary to understand it. What I'm doing here, I call these wiggle diagrams. I draw the numerator because it's a polynomial, it's easy, parabola. I draw the denominator, it's a cubic, it's not too tough once you understand that, okay? And so then I look at the values I see here. Notice that the numerator function's positive out to the left here, and the denominator is negative. Positive divided by negative is negative. And notice the end behavior, x squared over x cubed approaches 1 over x, doesn't it? Which means it dies towards 0 off over here. So I know the graph is going to come in like this over here. As I go off to the left. Now in here, there's a vertical asymptote here. Can it do this? Can it cross that vertical asymptote? No, has to take a dive. It can't ever touch that vertical asymptote, so it has to do this over here. Now, look in this region in here, folks. Positives divided by positives. And near a vertical asymptote, it has to either blow up or blow down. So it has to blow up on this side because of the nature of positive divided by positive. And then we've got a 0 here. 0 here. And then in this region now, we've got positive readings divided by negatives, or vice versa. Negatives divided by positives are negative. And here's your y-intercept, folks. And so it has to do this. And then what? Here's a vertical asymptote. Negative divided by positive has to stay negative, doesn't it? Has to dive down there. I'll start the next class session out with this graph more carefully done. And then finally, over here, positive divided by negative has to stay negative, has to come up through here. And then out to the right, notice positive divided by positive has to stay positive, so it has to sweep in like that and approach this horizontal asymptote out there. So the graph is, sorry about all this, it's this thing. This, that, and then coming up here like this, and dropping out like that. How do I check to see if we have it right? We put this fancy thing in our calculator with an appropriate viewing window based on these numbers we see here, not too far to the left, not too far to the right, and you should see that picture. I'll start the next class session out with this function with a little more explanation. Okay, that's it for today. See you tomorrow at 10.